So thank you, those of you who woke up bright and early this morning for day 2 of Big Data. Our first speaker is Laura Kreidberg, who's a junior fellow at the Harvard Society of Fellows. She's also an ITC fellow at the astronomy department. Before coming here to Harvard, she finished her PhD and master's at Chicago, and prior to that, her bachelor's at Yale. She, like many of our other speakers, is exceedingly awesome and exceedingly decorated. Therefore, a subset of her fellowships and accolades include, I didn't check the pronunciations on any of these, the Paul Hurt-Lendy, this is the PH Lectureship at the Harvard-Smithsonian Center for Astrophysics, the International Astronomical Union Division F PhD Prize. She was awarded both Hubble and Sagan postdoctoral fellowships, as well as the Roger Doxey Travel Prize from the American Astronomical Society. She's part of numerous sort of like large-scale cross-institution collaborations in astrophysics, including the Breakthrough Starshot Science Team. And on top of that, she's designed a number of sort of exciting open-source libraries with truly exciting-sounding names. And while I don't understand any of the technical details, I'm very, very excited to learn about, Spider-Man, her open-source system for modeling phase curves and secondary ellipses. I should also say, we overlapped at the Society of Fellows, and she's just a totally and completely amazing person, and she studies aliens. So we're very excited to hear about small data, big ideas, inferring the presence of extraterrestrial life from a few photons. Let's welcome Laura.
All right, thank you, Scott, for that introduction. It was a mouthful. And thank you guys for getting up early to be here this morning. As Scott said, I am going to be talking about aliens, but maybe not in the way that you might expect. And I've noticed that all of the speakers yesterday seemed to have some anxiety about whether their data sets were big enough. And I feel like I can stake a claim to maybe the biggest data set of all, which is all the stars in the universe. We know that there's about 100 billion stars in our Milky Way galaxy alone. And on top of that, there's about 100 billion galaxies total. So that gives you 10 to the power 22 stars to choose from. And my task today in this talk, and also in my career, is to try to whittle down this sample to try to find stars that have inhabited planets around them. And so I'm going to be talking about how we find those today. So the question is there any life out there besides the life that we see on Earth? And I want to talk at the beginning about a little bit of historical context for this. So people have been wondering whether alien life existed starting, forever ago. And it was quantified in this framework the first time in the early 1960s by a guy named Frank Drake, who put together what's called the Drake equation. This is me and Frank Drake on the right there. I got to meet him at a conference. And he said that the number of civilizations where we might expect to have radio contact, so that would be a sign of intelligent life if these aliens are communicating via radio, is equal to how fast stars are forming in the galaxy, what fractions of those stars form planets, how many of those planets are habitable, and I'll get back to what that means in a minute, what fraction of those planets actually do go on to form life, how often that life becomes intelligent, how often we can actually detect that intelligence remotely, and how long those civilizations last. And so when this was first formulated in the early 60s, none of these terms were known, except maybe the first one. And so it was sort of a thought experiment at the time. But we've started to be able to fill in the detail, and we've also modified it to extend beyond radio. So why was radio so popular to begin with? It's actually sort of a historical accident, I would say. It started in the 1920s when Mars happened to align very close to the Earth in its orbit. And radio technology was fairly new on Earth. It was developed in the early 20th century. And so what people thought is, if the aliens are on Mars, surely they've developed radio technology a long time ago, and the moment to try to contact them is when we happen to be close by. And so this was a huge big deal in 1924, and the US military called for a week of national radio silence, and they called on the chief cryptographer of the Navy to decode the possible Martian messages. Needless to say, they didn't hear anything back, unfortunately. But that didn't stop people from searching. So this is the Allen Telescope Array, which is part of the SETI project, Search for Extraterrestrial Intelligence, just like the movie Contact. And so people have been searching for radio signals for decades. Radio is attractive for a number of reasons. It easily permeates the Earth's atmosphere, and we expect that that would be true for many other atmospheres as well, so it's a logical thing to be communicating with. However, we haven't heard anything. So this is essentially a failed experiment. And it gives rise to the question, well, if there are so many stars in the universe, and if life is common around them, why have we not heard anything back? And there's a whole bunch of reasons why not. One very obvious one, I think, is that radio might not be the best choice. In fact, that's what we're seeing on Earth, is that we're transitioning towards satellite communications over radio very quickly. And another factor, I'll skip over the space travel is hard, that's sort of a separate argument. But another factor is that intelligent life might not stick around for very long. That's sort of macabre, but just to put it in perspective, the yellow dot in the upper right here is the size of Earth's radio bubble. That is to say, how far our radio signals have traveled in the galaxy. And this is it blown up here. So our radio bubble is about 100 light years in radius. The galaxy is orders of magnitude larger than that. And so even if there were other civilizations out there listening for us, our signals have just not had time to travel very far. So this has led, after all of these decades of failed radio searches, this has led a lot of people to think about alternative ways to search for intelligent life elsewhere. And one of these people is Sarah Seager, a colleague of mine down the road at MIT. And she developed an update to the Drake equation that I have called the Seager equation. She didn't name it after herself, but I'm allowed to do that. And so she wants to answer the question, how many planets have detectable signs of life? So she's relaxed the requirement that it has to be intelligent life, and just said life at all. And so her equation says that the number of planets with detectable signs of life is equal to how many stars we can search, how many of those stars have habitable zone planets like the Earth, the fraction of those planets we can look at in detail, and I'll get back to that later in the talk, times how many of those have life on them. And this is the really tricky part, is what fraction of those actually produce some kind of signature. And we're talking about biosignature gases here. So on the Earth, the example is that we have oxygen and methane in our atmosphere. Oxygen is a very, very reactive gas, especially in combination with methane. You put oxygen and methane together and you get water and CO2 out. And so there has to be some source of production to keep both of those gases in our atmosphere in the concentrations that we observe. So for the rest of the talk, I'm going to walk through these terms, which really excitingly, we finally know what a lot of them are. Some of them we don't, so I'll speculate wildly about those. And at the end, I'll provide a number for how many inhabited planets I think that we can realistically detect on a timescale of our lifetimes. Okay, so the first question is, what fraction of stars actually have habitable zone planets? So the habitable zone is this region around the star where the planet would have temperatures appropriate for liquid water to exist. Some people really don't like this definition, but I think it's a good starting point. Water is everywhere on Earth that has water. Life also exists. Water is a great solvent for chemical reactions that would help develop the complex molecular structure you need to start forming intelligent things. And so I think it's a reasonable starting point. And we didn't know how many habitable zone planets there were until very, very recently. And a lot of it is thanks to NASA's Kepler mission, which was launched in 2009. So this is a picture of Kepler. On the right, there's a person working on it, so you can see the scale down at the bottom. And the way Kepler works is that it stared at a fixed field of view in sky, monitoring the brightness of about 150,000 stars, searching for transiting planets like this one. So these planets are too far away to spatially resolve them from their host stars, but we can infer their presence by observing a drop in the brightness of the star during the planet's transit. And for a Jupiter-sized planet, the amplitude of that drop is about 1%. For an Earth-sized planet around a sun-like star, it's about 90 parts per million. So these are very, very small signals. And Kepler, let's see if this works. Hold on. Yeah. So Kepler, this is the Kepler orrery, which is just an illustration of all of the planets that have been detected. Oh God. Can you take that? Thank you. So this is courtesy of my colleague, geography. And you can see the time in the upper right there. So this is units of days. So really sped up. Every single one of these systems I could give an hour-long talk about. I'm not going to do that today. But we've seen an enormous diversity of planetary systems. Almost every star has at least one planet. Many stars have multiple planets. We've seen planets for much shorter periods than these orbit the solar system. Some of these orbital periods are so short that the planets actually orbit in less than a day. So incredibly hot. Some of these are terrestrial planets that are so hot that their surfaces are melted into lava. And so while this is exciting, every one of these is a really fun system. The goal of Kepler was not to discover exciting individual systems, but rather to measure the occurrence rate of Earth stars, how many Earth components are out there. And I didn't time it right. I was trying to time it until exactly the end. All right, here we go. That's it. All right. Okay. So the punchline is that Kepler was a huge success in measuring how many planets exist around other stars. And this figure is the state-of-the-art in planet occurrence measurements. This plot actually recently won, the grad student who wrote this paper recently won the award for the best PhD thesis in North America for this past year. And what you can see is a couple of very noticeable trends. So large planets are much less common than small planets. The y-axis is the number of planets per star on average, subject to the constraint that the orbital period is less than 100 days. We just didn't have enough time to search for longer. And here's planet size on the x-axis. Neptune is about 4 times the radius of Earth. Jupiter is about 10 times the radius of Earth. So these smaller planets are really much, much more common. We see a peak of things around 2.5 Earth radii that we have no idea what these things are. The solar system doesn't have one, so that's a big mystery. But for the purposes of this talk, I want to focus on this peak, which is incomplete below about an Earth radius. Those planets are just too small to see. But what we're seeing is that that Earth-sized planets are very common. And if you do some extrapolation, you can infer that about 1 in 10 stars has a planet the size of Earth with a temperature appropriate for liquid water to exist. So that's our second term here, the fraction of stars with habitable zone planets. We know now that that's about 10%. And this is new as of the last few years or so. Okay. So the second part of this is how I'm going to address all 3 of these terms at the beginning here. How many of these planets can we actually look at? And one approach to doing this is to search for planets that are around the smallest stars. And the reason we're interested in doing that is that the smaller the planet is, the smaller the star is relative to the planet, the easier it is to study the signal from the planet itself. Another reason is that small stars are actually the most abundant in the galaxy. They outnumber sun-like stars by a factor of about 3 to 1. So the sun in this diagram is one of these yellow circles. There's about 20 of those in the solar neighborhood within 10 parsecs or so of us. Most of the stars are much smaller, and so a lot of folks have been focusing on the smallest stars, searching for planets around them. I'll skip that. And so I don't know if you followed this in the news, but the short story is that we've seen many exciting planets. And so exciting, in fact, that it made the Google Doodle last summer. Did you all see this? Yeah. Yeah. I really identify with the moon in this animation. And so this was in reference to the discovery of 7 terrestrial planets around a nearby very small star. The star is basically the same size as Jupiter. And so even though these planets are small, the radius of the star is also small. And so when they transit, it causes about a 1% drop in flux. Excitingly, that's not even the only system. So this is an incredibly rich single star that has 7 terrestrial planets orbiting it, including 2 that are in the canonical habitable zone. There was also a discovery of a habitable zone planet around Proxima Centauri, which is our nearest star. In addition to this, there have been a number of others, totaling about a dozen of terrestrial planets around the smallest stars, and 3 or 4 of them, depending on how you count, are in the habitable zone. So already now we're starting to find the planets that will be our best chance for searching for biosignatures. And TESS, which NASA just launched successfully in April, is going to scan the entire sky, searching only the brightest stars to clean up on this. And so they're expecting to find about 10 more of these systems on a timescale of the next 2 years or so. TESS, it launched so recently that the data aren't available yet, but I've been getting information from my friend who's not in the control center, but whose office is next to the control center, and so he assures me that everything is going great. So that's really exciting for us. Okay, so that gives us a couple more terms here. So if we look at how many observable, so nearby, habitable zone rocky planets we have access to, the answer right now is 3 or so. We expect about 10 more in the next year or 2. And the long-term goal for NASA is to find about 100 habitable zone Earth-like planets that will be capable of studying the atmospheres. And so this is not something that will happen in the next 10 years, but maybe 20, 30 years from now, NASA's next generation facilities will be capable of this. Okay, so I want to transition now to some more speculative stuff that I thought would be fun to share with you. We all want to know what fraction of these planets actually have life. And I'm going to present both sides of the argument, one argument that life is rare and the other that life is common, and I'll let you decide what you think is more accurate. And I'll start with the argument that life is rare. So this is, they call these people rare earthers, who point out all the things that are very special about Earth and say that each one of these things is a requirement for having life develop. So one of them is that the temperature has to be right for liquid water, so we all basically agree with that. That means you can't have too much greenhouse warming. You want to have a fairly stable orbit with a fairly low eccentricity, so that the temperature of your planet remains very stable. You don't want your star to be too active, not too much stellar flaring, which can disrupt your atmosphere. You also don't want your planet to be totally tilted on its side or rotating too rapidly, because both of these things will contribute to greater inhomogeneity in your temperature. In addition to that, people have argued that you might need a planet like Jupiter to protect you from asteroids. So Jupiter is so massive that it attracts asteroids, and so we think that it's kind of a shield for us that protects us. It might need to be located far away from the galactic center. There's all kinds of things happening there that are bad for us, including the fact that there's a higher density of stars, and that can contribute to your planet getting kicked out of its orbit, so that's bad. So there's this notion of a galactic habitable zone that's about 2/3 of the way out from the center, which is exactly where we are. You might need plate tectonics for geologic cycles. So we know that to get rid of CO2 in our atmosphere, we weather the rock, and then the rock is subducted, and so that's how we prevent a runaway greenhouse, at least for now. And And so the list goes on. There's a lot of things about Earth that seem very, very special that we might want to require for an Earth analog to also be considered habitable. On the other hand, now I'll present the argument that life is actually common. And so one point about this is that it's really, really easy to create the basic building blocks for life. So back, I think, in the 1950s, Stanley Miller did an experiment where he tried to simulate the conditions early on in the Earth. So he boiled some water and he put some basic stuff in there. So I think there was ammonia and methane and carbon dioxide and some sulfur and all the things that probably existed in the early Earth. He boiled it because the early Earth was very hot, which formed steam, which he then shocked to simulate lightning. And then he collected the molecules that formed in that reaction. And he found that just in that very, very simple experimental setup, he produced 11 out of the 20 amino acids that we need today. So it's really easy to start building these molecules that life uses. Another argument is that life formed very, very early. So as soon as the Earth was cool enough to have oceans, essentially, is when we start seeing the first microfossils. So these are about 3.5 billion years old, the first evidence that we know of for life to exist. The Earth is only about 4.5 billion years old. So as soon, and for much of the first billion years, it was just sort of magma and really hot. So there would be no place for life to evolve. We also see evidence for very extreme life on the Earth. So we see extremophiles that thrive in very acidic environments, very basic environments, hot, cold. My favorite is actually the tardigrade, or the water bear, this thing on the right, which is not technically an extremophile because in its natural state it lives in ponds and under tree stumps and stuff. But this thing can survive the most outrageously inhospitable conditions. They took tardigrades up to the International Space Station, put them outside, like in the vacuum of space, and then brought them back to Earth, and they like woke up. One of them even reproduced. I think it was pregnant. And the way they do this is that when they're exposed to harsh conditions, they sort of crystallize themselves in this amber-like substance, which can protect them from anything, vacuum, like radiation, no water, cold temperature, high pressure, you name it. There was another experiment where they froze one for, I think, 30 years. And then they warmed it back up, and it just like kind of got up. It was a little slow, but it just swam around. It was fine. And so that, to me, is a sign that life is insanely resilient, and that there are a lot of ways that nature can be creative for life to exist in environments that we might not consider to be particularly friendly. Earth has also survived really, really dramatic changes to its climate. So in the early history of Earth, the sun was about 30% fainter than it is today. The atmospheric chemistry has changed enormously, in part due to oxygenation, which is from life. We've had asteroid impacts. So I don't know if, like, I feel like we get kind of blasé about the asteroid impact that killed the dinosaurs, but if you read about it, it was like so bad. Like the asteroid, the amount of energy that was released was 6 orders of magnitude larger than the largest bomb that has ever detonated. It's thought that the impact triggered mega tsunamis with height over 100 meters. The ejecta from the impact were basically launched into space and then upon re-entry heated up and broiled the forests, which ignited massive forest fires. Meanwhile, there were earthquakes, there were volcanoes. The volcanic eruptions released so much ash that the skies grew dark and disrupted photosynthesis. And yet, the dinosaurs didn't make it, but other life did. Okay, so, and the Rolling Stones made it through the 80s. All right, so I think, for me, I'm optimistic that life is very common, and so I would guess that order of magnitude life arises on every planet where it's possible. Okay, so in the last little bit of my talk, I'm going to describe how we're actually going to detect this life. And so as I mentioned before, biosignatures are the things we're looking for. So this is a spectrum from the Earth's atmosphere. This is bounced off of reflected light from the Earth bounced off of the moon. And you can see absorption features from ozone, from oxygen, from methane. And we want to know whether we can actually detect these in the atmospheres of exoplanets. And the way we would typically do this is observe the transit of a planet as a function of wavelength. So we split the light into a spectrum. And at wavelengths where the atmosphere is more opaque, the planet appears larger, and so the transit depth increases. The amplitude of these features for an Earth analog is smaller than 10 parts per million. So this is an insane measurement challenge. Just to illustrate a little bit more, this is a real picture of the Earth from, I think this might be the International Space Station. And so here's the Earth at 8.6 microns. Here, this is the moon. And then if you look at 9.6 microns in the ozone band, you can see that the Earth looks bigger. So this actually works. But it's a tiny, tiny, tiny signal, especially if you're looking at it from something that's like 40 light years away. Okay, so just a teeny bit of data. This is to show that this technique actually does work. This is a paper of mine where we looked at a Neptune-like planet. This absorption feature is due to water. So this is proof of concept that for larger planets that are a little bit easier targets, these techniques work like a charm. But for Earth analogs, their signals are quite a bit smaller. And so we want to know exactly how big of a telescope are we going to need to actually be able to detect it. And so this is a paper I wrote with my colleague Caroline Morley, where we looked at planets that have been discovered already. And we said, okay, let's make some plausible guesses about what their atmospheres are like and then calculate whether we can actually detect those atmospheres or not. And so we used the Earth, Titan, and Venus as end cases for what the atmosphere could be like. We know that the atmosphere depends on a lot of things. It depends on outgassing due to volcanism, what volatiles are delivered by comets, etc. Has any of it photoevaporated over time? We don't know, and so we just used the solar system as inspiration. And we found that, and then we assumed that using the James Webb Space Telescope, which is NASA's successor to Hubble, scheduled to launch in just a couple years, could we actually detect those atmospheres with that facility? And the answer is yeah. So here's an example of one of the TRAPPIST planets. This is the hottest one, so it's the easiest. And these different lines correspond to different atmospheric compositions. So this red one is a carbon dioxide-dominated composition. The blue one is water. And the orange one is methane. And so you can see that with just 6 transit observations, which is very reasonable, it's not very much telescope time, we'll start to be able to distinguish spectral features for different molecules in these planets' atmospheres, which is really exciting. Okay. And so that's a starting point. That's not, notice that I didn't say we're going to detect methane and oxygen and ozone, but we'll start to get a first idea of whether these planets even have atmospheres or not, which we currently don't know. And so finally to end, I'll say this is all great, but I think the really tricky part is even if we measure an excellent spectrum for an Earth-like planet, how often will we be able to infer that it actually has life, that it's truly a biosignature that we're seeing? And I'll offer a guess. I don't know. I think we have one example, the Earth, where the presence of life has clearly shaped the atmosphere. There are other factors that could shape the atmosphere as well. For example, volcanoes produce a lot of gas. If you have a star that's very bright in the ultraviolet, that can break up water molecules. The hydrogen will then evaporate because it's light and you're left over with oxygen. So oxygen by itself may not be a perfect biosignature. But I would say, so order of magnitude, it can't be 0 because we have one case where we see evidence for biosignatures. It can't be 100% because there's too many false positives, so call it 1 to 10%. Call it 10%. And what that leaves you is assuming we get our sample of 100 from NASA, which is a long-term NASA goal, and they're all inhabited, and 10% of the time we can infer definitively that the signal we're seeing is some kind of disequilibrium chemistry due to life. That'll give us about 10 planets in our lifetimes that may be inhabited. So I'll leave you with that. Be happy to take questions.
So far, other than Earth, we have not had any other affirmative evidence of life. Is that right? Still?
No. Yeah, that's the short answer is no. We know that there's a lot of good environments for life to evolve, but so far, nothing. And no alien visitations. Like, I haven't been abducted by aliens. I get that question frequently.
That is, of course, exactly what the aliens would have trained you to say if you hadn't abducted. Very good.
So feel free to laugh. But what are we doing to make ourselves observable to other planets?
Oh, that's a good question. So it's funny, the opposite of that has actually been discussed more, like how we hide. Because people have said, including Stephen Hawking actually said, if you look at the history of Earth, anytime a group of people was recognized by some foreign entity, they were invaded and conquered and destroyed. And so people have talked about laser cloaking, which the idea is that we would shine a laser at the exact same time the Earth was transiting from the point of view of another star to mask our transit signal. Things like that.
All right, one further question. So, is there any way, I realize we're talking about very, very, very small n, but is there any way to get like more precise sort of distributional estimates, like where we should be looking or anything like that?
At this stage, we're sort of in the take whatever we can get mode. But yeah, some of them more, like if you keep the focus on Earth-like life, which is fine as a starting point, you could use some of the rare Earth arguments and say, okay, let's look at systems where there's also a Jupiter-like planet. Let's try to find systems where there's also a moon, things like that.
That's super cool. All right, any further questions?
I was curious if you could talk a little bit more about the occurrence rate of Earth-like planets from Kepler. I mean, I know that one of the sort of saddest things about the mission was that it never really got to measure that very accurately, and so fundamentally you're left extrapolating from the data we have. How robust are those estimates now? I mean, a couple years ago, people like Dan Foramaki were saying that, one number, and I've seen that number sort of fluctuate by orders of magnitude in the subsequent years.
Yeah, that's a really good question that I kind of glossed over. I think people are converging towards an answer that's in the 5 to 15% range. So it's not like 100% and it's not 1%. So that's why I picked 10. But I think that there's actually some novel methods that have been applied to the Kepler data set, including using neural nets to search for transit-like events that have been really promising. And in fact, I don't know if I'm allowed to talk about this, but a friend of mine has a candidate, Earth 2.0, from the Kepler data set. So it may be that the planets actually are there, lurking in the noise, and that further analysis can find them. And that'll help us refine that estimate.